Our analysis of this circuit with two resistors one after the other, an arrangement referred to as a series combination, shows us something very interesting when we look at the structure of our equations. If we compare this to our original very simple IR circuit that had a single resistor, if we go all the way to that initial analysis, up here we had it, right? The equation that we came to was that E, the potential from the battery, the EMF of the battery, was just compared to I times the resistance here, in this case of a single resistor. In the case which we've just solved, we find exactly the same mathematical form, current times a resistance minus the final EMF, but now the two resistors seem to be combined into something that's just equivalent to the original combination, except now if we were to, for instance, replace this series combination of resistors with a single resistor whose resistance was the sum of these two resistances, clearly we would get the same current flowing through the circuit. So this leads us to a second way, a convenient way of analyzing circuits that is much more convenient mathematically than going through all this Kirchhoff's analysis. You can't always use this method, but it's so powerful and convenient, it's worth studying in and of its own right. So let's take a look at this. This is the method of equivalent circuit elements. Now, so it's the method of equivalent circuit elements. And the basic idea is just what I have just expressed. What you do is you see if you can replace elements in a more complex circuit, such as this where we had these two resistors, and replace them with a single circuit element. In order to sort of formalize this kind of an idea, we need to define the concept of a circuit element. What exactly do we mean by this? Well, it's just a singular circuit element. If I want to give a definition of a circuit element, it's a device, an electrical device, of course, which has terminals, and it's actually those terminals that the device interacts with the outside world. Those terminals, as the name implies, would be your connections where the device ends. Those are your connections to the outside world. And now these terminals have a certain set of currents flowing through them, I's, and they have voltages that you can measure between them. So it has I's and V's. And the next key thing that it has to have, and this is very important, it has to have some characteristic relation among the I's and the V's. So there's some characteristic that describes the circuit element. It has some signature, if you will, relation among the currents that will give you the voltages in terms of those currents. The classic example of a circuit element then is the resistor that we've just been studying. In the resistor case, what you have is that the upstream voltage is equal to the current flowing between the terminals then times this proportionality constant, the resistance. We also have among our list here the battery, and in this case the voltage of the battery, the upstream voltage again, measured from the minus to the positive terminal in this case. Actually, I shouldn't call it the upstream voltage because it really doesn't matter which direction is upstream or downstream. It's just the voltage from the minus to the positive terminal is always a fixed constant determined by the chemical reaction, E. So that's the idea of a circuit element. Let's now try to apply this to the idea of our resistors in series. So if we want to make an example of this, let's consider now, for an example, the series combination that we were just considering. If I go and I look at my circuit, right, I went from this point C, near the top of the circuit, right, to this point E. And the idea now is I want to cut these two resistors out of my circuit and try to view them as a circuit element of themselves. So I'm just going to take everything between C and E out of my circuit and try to study that and replace it with some kind of an equivalent element. So here is point C. Then below it I had my resistance R1. Then there was point D in the middle. And then there was resistor R2. And then there was point E. And what I'm doing now is I cut those out of the circuit, and I'm going to enclose everything between C and E inside and treat it as some kind of new sort of a circuit element. So now the characteristics of this thing are that some current I may come and flow through this lumped unit, that is whatever is inside these dashed lines you could consider as a black box. And I want to know now what is the characteristic? What is the upstream voltage of this mysterious circuit element that we know secretly is made out of two resistors, one wired in after the other? So I'm going to replace that combination and just ask, well, is there something I can put inside here between C and E that is equivalent and will always have exactly the same characteristics as this original combination if I send a current I down through there? Well, let's see. What is this then, right? This is the particular voltage, upstream voltage, as I go from point E to point C. And this should be some kind of function of the current flowing between my terminals. And the question is, well, what is that particular voltage? Well, to analyze this, we can use what we know about voltages. The voltage going from E to C is the sum of the voltage going from E to D and then from D to C. So that is the voltage to get to D from E, and then the voltage to get finally to our destination C from D. And those voltages, we know, then depend upon the current flowing through each of these resistors. By Kirchhoff's first set of laws, we know whatever current I is flowing down into resistor 1 through terminal C will eventually all enter resistor 1, flowing in the downward direction. And that current, again, after it goes through junction D, what comes out of D will again be that same value of current flowing down then through resistor 2. So I now have a presumed direction of current flow. I immediately label the plus and minus sides, the upstream and downstream sides of my resistors. To V from E to D, the voltage from this downstream side to this upstream side, I'm going against the current. That's going to be positive. It'll be the current that's flowing through R2, which is the external current flowing through the whole device. So that will be I times R2. The current going from, the voltage from D to C, similarly, is going to be a plus as I'm going upstream, and it's going to be I times R1. So I can see that my characteristic relation is that I get a positive current times some proportionality constant, which we've just worked out is R1 plus R2. At this point, we can look at this and say, oh, wait a minute. This equation, V up equals I times some resistance, that just looks like the standard terminal characteristic for a resistor of a particular resistance, which we might call R sub EQ. It's some equivalent resistance to the original combination. So I can replace this combination then with a black box that consists of a single resistor with resistance Req, where that value of Req, clearly, to make the equations align, is the sum of the two resistances, R1 plus R2. And if I do that, I will have exactly the same presentation for this equivalent resistor to the outside world as I did for that original combination. So this is our final result, basically. The equivalent circuit element for a series combination of resistors is another resistor whose resistance is the sum of the series resistances. So in this case, what we would say is we have a, quote, series combination, and the result of a series combination of resistors is that the equivalent resistance is just the sum of the composing resistances. Now, we've been calling this a series combination, and it's a very common type of combination. It's worth formalizing that a little bit. What we mean by series combination, what made this whole derivation work, you'll notice, is that the current in every single element, I, was just equal to the external current that was pushed through the device, right? The two resistors had exactly the same current because they were wired in series. Whatever flowed through one had to flow through the other. The other key point here had to do with the voltages. In this case, the voltages across each of my elements had to be added together to give me the final external voltage. So then we would say that in a series combination, you sum the internal voltages in order to get the external voltages. And that's a more formal definition of what we mean by a series combination.